Good morning or good afternoon, depending on where you are at. My name is Atarot Azizin Amini, Director of the IBT, ABC UTC. Before we start the presentation, couple of news. For the 2024 World Bridge Engineering Conference is now out. You can go to our website and submit your one-page abstract. This time, we are covering every aspect of the bridge engineering. It is not just ABC, it's everything related to the ABC. So if you go to our website, you will see some examples of the conference topics that will be covered. And the deadline, again, is actually next year, April 12, 2024. But please, if you see good projects that you have that fit some of the topics that we have, please go ahead and submit. And again, we hope to see many of you during the World Bridge Engineering Conference. And there's also opportunities to exhibit. So at this point, I'm going to turn the screen to Kathy Kroll, who's going to share with you some additional news related to the IBT, ABC, UTC, and the bridge engineering. Kathy?
Thank you, Torad. Welcome to today's webinar. We will be learning about steel bridge rehabilitation using UHPC to repair corroded steel beam ends. By way of description, rehabilitation of our aging steel bridge inventory is a common topic of discussion in the bridge community. The primary source of deterioration of steel bridge beams is leakage through failed deck joints, resulting in corrosion and section loss at the beam ends. This webinar covers the research and implementation of an innovative, rapid, and cost-effective way to repair corroded beam ends using UHPC. The research was funded by Connecticut DOT and undertaken by the University of Connecticut. This resulting technology was implemented on a bridge carrying I-91 in New Haven, Connecticut. The presentation will include research results and lessons learned from field implementation. Our speakers are Michael Culmo and Alexandra Hain. Mike Culmo is a bridge engineer with over 35 years of experience in the design of steel, concrete, precast concrete, and timber bridges. He's the chief bridge engineer at CHA Consulting Incorporated, who is responsible for the development and deployment of new technologies in the construction market. He has special expertise in the field of accelerated bridge construction technologies and constructability engineering. He's the principal author of numerous publications in the field of accelerated bridge construction, including the 2018 AASHTO LRFD Bridge Specifications for Accelerated Bridge Construction. Mr. Culmo has served as an adjunct faculty member in the Civil Engineering Graduate School at the University of Connecticut and is the current director of the Certificate Program in Bridge Engineering. Mr. Culmo holds a bachelor's degree in civil engineering and a master's degree in structural engineering, both from the University of Connecticut. He is a licensed professional engineer. Dr. Alexandra Hain is an associate professor in the Department of Civil Engineering at the University of Connecticut. She received her PhD in civil engineering with a focus on structural engineering in May of 2019 from the University of Connecticut. Her research focuses on novel construction materials, innovative inspection and repair techniques, as well as engineering education. Mike and Lexi will be joined during the question and answer by Paul Lyles, who is the former bridge engineer for the Georgia Department of Transportation, and Rick Liptek, who is the chief bridge construction engineer at Michigan Department of Transportation. Mike, I'll let you take it from here.
Thank you, Kathy. I take it you can hear me fine. So we're here today to talk about an interesting way of repairing corroded steel beam ends using ultra-high performance concrete. Sounds like an unusual topic, and it is, but it's a very useful topic in preserving our steel bridges and extending service life of steel bridges. So this is an overview of what we'll be talking about today. We're going to cover the whole gambit from the initial inception of this idea to the research that was undertaken to prove the idea, and then we'll go over several pilot projects where we've actually instituted this repair on actual bridges, and we implement this research into real-world bridges, and then we'll cover some key findings. So this is a photo that most bridge engineers are probably familiar with. It's really not a bad sign for steel. It's a bad sign for leaking deck joints. Leaking deck joints are the primary source of major corrosion on both steel and concrete bridges. In this case, a steel bridge. And this photo shows a typical beam end that we see for older bridges, especially beams that are on the fascia near the gutter line where the most of the water is coming through the joints. What happens is the water debris piles up in the bottom flanges, the water comes down, splashes, and usually the typical pattern we see is the bottom 6 inches or so of the web is corroded and quite a bit of section loss on the flange, and sometimes 100% section loss on the bearing stiffeners. So this is the issue we're dealing with. The real issue is shear transfer. The flexural capacity is, even if we lose a significant portion of the bottom flange, the bending moments are so low at the end of the beam, it really doesn't affect performance. But shear transfer is the major issue we're dealing with here, and to accommodate the bearing reaction forces and transferring those into the girder. So how do we currently repair this? We see pictures like this from all over the country. It's very common to clean the steel, bolt plates on, bolting angles, plates. Sometimes we're cutting portions of the flange away. Sometimes we're welding, we're painting. There's an awful lot going on these beam ends. And we've seen repair costs for some of these beam end repairs exceed $30,000 to $40,000 per beam end. And on many of these projects, we're jacking the bridge to remove plates. And the center photo shows a jacking frame that we might see with jacking equipment, and a significant amount of time and effort to do that. And the photo on the right shows a repair in progress, many holes, lots of plates being bolted on, in some cases welding plates in place, all very expensive. And so the idea here with this research was try to come up with an innovative way to repair beam ends without jacking the structure, to come up with a repair that is structurally sound, but also, importantly, stops future corrosion. Because this kind of repair, you can come in and do a steel repair, and in 10 years, you might be back repairing it again. We're trying to get a repair that's more long-lasting and durable. So where did the genesis of the idea come from? It actually came from me many years ago. I worked for the Connecticut DOT, and the photo on the upper right is a photo of 2 bridges in New Haven, Connecticut. Interestingly, both bridges have been replaced, but this is the photo from the 1980s, showing the bridge in the foreground is a bascule bridge, a twin-leaf bascule bridge. The approach spans were riveted steel plate girders. The fascia girder was had a concrete encasement, but these girders were resting on the support pier for the bascule span, and the ends of the beams were virtually uninspectable the way this thing was detailed. Our inspectors went out there and found literally 100% section loss on every beam end. To this day, we're not sure why this bridge didn't have a more major failure, but it was discovered and we had to do an emergency repair. And the idea we came up with was essentially to convert the last 10 feet of the beam into a reinforced concrete beam. We essentially encased the beam in concrete with a lot of reinforcing steel, and we essentially converted it to a concrete beam end. Very successful repair, worked very well. Well, then UHPC has come along, which I call liquid steel. Very high strength material with tensile capacity as well as compression capacity. And the idea we had was maybe we can use UHPC to do a similar but much simpler approach to repair steel beam ends that are corroded. Again, our goal was to eliminate jacking, cutting, welding, and bolting of beam ends, to simply go in and pour some UHPC to repair and restore the shear capacity of the beam. So this is the genesis of the idea, and Connecticut DOT asked me about ideas for research, and this is one that I came up with. And I give Connecticut DOT a lot of credit. They funded a research project to study this, and then the University of Connecticut was selected to execute the research to prove the viability of this concept. So with that, I'm going to turn it over to Dr. Hain to talk about the research that was done on the projects where we implemented this idea.
Great, thank you so much. So let's kick it off with first understanding what this repair looks like. So we can see a beam end with that darker kind of corrosion that reminds you of one of the earlier slides. The first step is to weld headed shear studs to the intact portion of the beam. So we want to clean the surface, weld these with just a stud gun, and then we can encase that full region in ultra high performance concrete. And what this does is create an alternate load path through the studs in the UHPC for bearing forces that bypasses that corroded region at the bottom. So this is that other example, but just looking at some of the pictures that we have from the field. So this is a beam in New Haven, Connecticut. This was the first implementation that we did, the full height. I'll talk more about this a little bit later. So here we can see our beam end with corrosion damage. We had full perforations in the web, close to full perforations in the bearing stiffener at both the top and the bottom. And the bridge, we cleaned all of the steel and then ended up going back and painting it. However, you can see the painting did not happen in the region that was going to be encased in the UHPC, because the UHPC itself provides protection. And then you can see the areas that are really well cleaned beneath those headed shear studs. After that, go back and weld the headed shear studs to those intact portions, so leaving that bottom alone. Then we cast and cure our UHPC and go ahead and remove that formwork. And you can see we're left with really simple end block of UHPC, and we're able to effectively translate those bearing forces. Some of the background on the UHPC material. I know a lot of people are familiar with UHPC, but one of the main questions that we get when it comes to this repair is, does it have to be UHPC? Could we do the same thing with regular concrete? And the benefits, we have done tests with regular concretes, the benefits of the UHPC really come in that durability and impermeability. So we do have the compression strength and the sustained post-cracking tensile strength, which are very important features. This is just a picture, of one of those UHPC cylinders, and we have those steel fibers. And that enables us to have no other rebar reinforcement in that cast. It's just the headed shear studs and then the UHPC material. And also, we really rely on that flowability. This allows us to work with more complicated geometries if we have larger skews or we have to use some tighter stud spacing to really be able to just flow around that and make sure that we have an end that's fully protected from future corrosion. Just a little background on the UHPC material, and I think this is just a great picture to show how different it is than concrete. If anyone has been on a project where you're working with UHPC or you've gotten a chance to touch it, mix it, it really is a different ball game, right? So it takes a while for the mix to turn over. And so if we have contractors that are not familiar with UHPC material, the answer can be like, oh, I think we need to add more water. It looks too dry. But this is the progression, and we see that different level of clumping. And then eventually, at the end, we're adding those fibers, and our final consistency is where we get that really nice flow. And that flowability is really important for the different ways that we can cast. So I'm going to go back pretty much to the beginning, starting about 10 years ago, which is after the idea came out about this research. What are the first steps to pilot it and really do some proof of concept testing to see if it was going to be feasible? So this phase of the research, Dr. Arash Zaghi was the principal investigator of that at UConn. He was the principal investigator for all three phases of research. And Dr. Kevin Zamitra was the lead PhD student on this. So there were third scale girder specimens, and here you could see two of them. This is the intact beam. This is the beam with simulated corrosion damage, and you can see we get that crippling at the bottom. And then we had one test of a partial height UHPC encasement. And what we were able to show here is that the beam not only didn't experience any buckling at the end, we were able to get a strength above that intact state. And another key part of that project was looking at our finite element modeling to determine what are those really specific design parameters that we have to look into further. And that led to phase 2. And I also want to give a shout out to Connecticut DOT. It was absolutely critical that they were involved in this research every step of the way, giving feedback, being in the lab for all the testing, seeing what needed to be done so that they would have the confidence to put this on a bridge in the field. So moving into phase 2, one of the first things that we had to do was investigate that stud capacity. We are relying fully on the studs to transfer the load to the beam end. So we're not counting on any residual capacity of the girder. So we need to make sure that we feel confident in the design of those shear studs, the number that we need, the size, and how that affects particularly a thin plate. right? Shear studs are used all the time for composite action with steel beams and a bridge deck. But what we needed to see was, how is that going to perform on a thinner web like this? And we did that through a series of push-off tests. So here we have just a steel I-beam section, and we're focused on just the transfer of load between the shear studs and the UHPC. And through this, we were able to refine the stud capacity equations, look at different things, what happens when the bond is broken, the full beam is exposed to corrosion, how do those impact the capacity? And that work was all led by Dr. Dominik Kruszewski. The second part of phase 2, and this is something that we get a lot when we're working with DOT, is they really want to see the full scale. Love seeing the smaller scale tests for proof of concept, but we needed to see the full scale tests. So this portion of phase 2 was led by Dr. Kevin McMullen, and we did studies on 3 full scale plate girder specimens. So over here, we can see this is some of the plywood formwork that was used to cast the beam end. And up here, we have a shaker, and this is able to apply vibrations, and that was used during casting and curing. One of the other main questions that we get is, we're saying that we're not going to jack up the superstructure. How is this going to perform? So we went out and collected vibration data from a local bridge and was able to feed that into our shaker and make sure that we were being able to simulate that live load during casting and curing. So you can see we did this on a full-scale plate girder. This is Dr. Kevin McMullen for scale. This was his PhD research. And one of the most challenging parts was looking at this simulated corrosion damage. In the first phase of the work, we just did uniform section loss. But as Mike mentioned earlier, that's not something that we see in the field. So being able to come in, and we did a variation of grinding and sandblasting just to make sure we were matching a profile. And this kind of profile of section loss at the beam end came from an inspection report of a bridge in Connecticut. And right here, we have this splice connection. So this left-hand portion of the beam, that's what we call our test end. We did this to be able to swap ends in and out to complete all the tests. And this was the permanent end of the beam. So here you can see the 3 different UHPC encased sections that we tested. So we looked at different heights. So this is what we considered a full height. So we did 2 full heights with different materials and also a partial height. And this is the test specimen in our full load frame in the structures lab at UConn. And these were fully instrumented tests. In here, we have a sample from the partial height. And what's really important, this shows subsequent cycles of loading. So the load is increasing from the left to the right. And we were able to completely eliminate any sort of failure at the beam end, and we were actually able to get that full tension field action. So moving on to phase 3, and this project is just wrapping up. This is where we focused on how can we translate what we did in the research. Everyone was very excited about the results, felt confident in the structural performance, but now how do we get that out there to the broader community? So we worked on developing a guideline for the repair to be posted online for Connecticut to use and to be shared with other designers, and also how we could actually help them on a pilot implementation to fully monitor the bridge and make sure that we had confidence in how it was performing. So here are the 2 implementations that the research team was involved in, and I'm going to be talking about both of these today. The first was on a rolled beam bridge from the 1960s. This was a plain carbon bridge, and we were doing a full height repair. This casting took place over October 2019 to May 2020 in a series of different casts, and we had some road closures associated with this because we were casting from the top of the deck. This was the first implementation. It was a consultant-led design. And in our second implementation, we learned a lot from the first. This was a plate girder bridge from the 80s, One of the main differences was this is weathering steel. So before we went out and did this repair, we also did another series of those push-off tests to just make sure that all the equations that we were using for stud capacity were still applicable when we were working with weathering steel. And we found that they were. This casting took place about 2 years later, and this was only a partial height, so we were able to cast from below deck with no road closures on above. So here's our first bridge in New Haven, Connecticut. They gave us a real doozy for the first bridge. It's always fun when you're working over rail, and we worked with particularly over electrified rail lines and freight rail. And there were beam end repairs on all 3 of these piers noted here. This is Interstate 91, so one of 3 major highway interstates in this state. And overall, we were repairing about 45 beam ends. So this is just another view from farther back. We had a composite concrete deck. One of the really unique parts about this bridge is we had variable beam sizes. The depth of the beams changed. We had different skews ranging from 25 to 35 degrees. We also had different end conditions. Some beams had bearing stiffeners and some did not. So the condition of the bridge was structurally deficient, and you can see some of those full perforations in the web. And of course, these 2 pictures here are from the inspection reports. It only got worse once we went in and cleaned it. So I'm fairly certain this might be the same location, and you can see how big that perforation was after we went back and cleaned it. So the beam ends, end diaphragms, connection plates, everything was severely corroded, and you could see we had really significant losses in bearing capacity, and we had some shear capacity loss as well. So talking about contracting, this was the first implementation of this repair in Connecticut. And I think it was really a model of, how can a group of people, the contractor, research team, owner, designer, inspector, really all work together and share lessons learned. So we worked closely with the designer to get any of the research data that they needed, the capacity estimations, and going back and forth on some of the design to make sure that there wasn't something that we encountered in the lab that they weren't considering. A couple of really unique components in the specification for the contractor is that the state did require a pre-bid meeting for all contractors bidding on the project. In this meeting, we came in and we reviewed UHPC material. We talked about the history of the repair, the research that we have done, and we also specified, the state specified the UHPC material supplier based on the research. And this is one of the biggest takeaways. If I can say it, I'm going to say it probably 3 times during the rest of this presentation, is if you're doing something new, make sure to include that mock-up, particularly if the people that you're working with do not have a lot of familiarity with UHPC. At this point, UHPC wasn't being used in a lot of other capacities in the state. So it was really important that everyone was on the same page and they were able to, the contractor selected was able to lead that mock-up to just get more confident. And another fun one, every contractor's dream, was that they had to provide access for our team to go in and do the instrumentation. So here's a couple of pictures from the repair design. The designer went with a 5/8 diameter stud, and depending on the condition, we had between 20 and 40 studs required per end. There's a few different design methods that can be used. For example, if you look at different suggestions in our guidelines, there's one where the studs are only really responsible for carrying the live load of the bridge, and others are we want to make sure it's really comprehensively designed, and our goal was to restore the original capacity. For the UHPC, the ductile JS1000 mix was used with 2% fibers, and this is something that was unique to the specification. They required the 28-day strength of 18 KSI. So all of our research was done achieving higher strengths. We did do some tests to show that the 18 KSI was more than sufficient to get the performance that we required. But this really came in that they just wanted to make sure that they weren't rejecting material, because you could see the complexity with some of these beam end designs, and working with a material like UHPC, it's not exactly easy to get rid of if something isn't working properly. So moving on to that mock-up, this is done in the contractor's yard, and this was their first example of trying what they had proposed for the formwork and the distribution system of the UHPC. So here is our steel beam and specimen. They just used plywood forms and bracing, and a PVC distribution system was used to enable casting from the top of the deck and filling multiple beam ends at once. So this top sheet of plywood is there to simulate the bridge deck, and we have this inverted cone. I know, Mike, you have a good word for it. It's a UHPC placement device or something. Worked incredibly well for the casting of UHPC. So they were able to just pass up those kind of 5-gallon pails, pour it in to the inverted cone, and that pressure head was enough to fill all of the forms.
It's the high-tech UHPC deployment cone.
All right, yeah, you get to patent that one. I love that name. And here is a view of the final mock-up. And you can see this is a little bit of a difference from the mock-up. This is the height of the UHPC that was stated in design. There was a gap there. However, when we actually moved to the field, some of the later pictures, you'll see we did end up casting all the way to that bottom of the top flange. So now moving into the field, working on the stud welding. So the first thing that's really critical that I want to know when we're looking at these weld collars is that we count on a complete collar around the stud. And we did have several issues when it came to having this kind of gap around in the top. And that's just something to make sure that the inspector is on board with, that they're looking out for. And we handled that by either adding additional studs, so we weren't counting on the capacity of this stud with the incomplete collar around it, or some of them went back and they were repaired with just some stick welding. So this is really important, and this is why we have to have that thorough cleaning of the place right underneath the studs. It's a really critical component. Here you can see just using that kind of standard stud gun to attach the studs. And here we have two representative views of a stud layout when we had a bearing stiffener and another when we did not. Moving on to some of our monitoring. So after the studs were placed, we did fully monitor 4 beam ends. And this is a view of our NEMA enclosure with our different data acquisition systems and all the wiring for our sensors coming in. So this is a view of one of the beam ends, and we had different gauges for being embedded in the UHPC to monitor the strain in the UHPC, strain gauges on the web and the studs to see how that was performing, other thermocouples to track how the UHPC was gaining strength to relate that to the temperature of the cast. So really some comprehensive monitoring, and we placed our monitoring on 2 different piers as well. With the forming, you can see this is once the decision was made to cast fully to that top of the flange, just a standard plywood forming. This is something that the contractor was great at. I do want to just point out that here we did have rods going through the web of the beam in 2 locations to tie those down to make sure that we weren't going to get any sort of blowout of the UHPC. We also had vent holes at the top of the form, and those got plugged once the UHPC was reaching the top. And just doing some simple kind of silicone sealing. So for those of you that worked with UHPC, we did specify a watertight formwork, and it's because once it starts going, it can be really challenging. So including these ties really helped us with not getting any explosive blowouts. And that was a huge concern since we were over the rail. And then this PVC distribution pipe went straight up to the bottom of that deck core. With mixing and casting, this was all completed on the top of the deck. And we had 2 of these mixers going at once. We did have the partial lane closures. The core holes through the deck were done in advance. So that was something that went really smoothly. And the UHPC was actually filled all the way to the top of the deck, and so no further deck repairs were required after casting. And here are the pictures of our cured beam ends. Overall, the project went incredibly well. You can kind of see that final view of when we had the stiffener and when we did not. And to show that we were getting the performance that we were expected, we looked heavily at our data collected on the repaired beam ends at different locations. And there's kind of 2 main things that we were looking for. So the first is if we're engaging those UHPC panels, and we did do instrumentation before the repair and after. So we wanted to see a reduction in the magnitude of web strain under live load events. And we really wanted to see that shift. So when we're getting that truck passage, how much strain is going into the web. And you can see before casting, we were getting around 200 microstrain. And then once we reached our 28 days after, we're now below 25. And this is really going to vary depending on what that initial strain is, how much deterioration we have first and foremost. But we did see a reduction in all of those high magnitude strain events. And one of the other things that we were looking for is that we wanted to just see a correlation between our strain measurements. So when we're getting a peak from a truck on the web, that we're also picking up that strain in both the UHPC and the studs. And we saw that on all ends as well. Now we're moving on to our second implementation. This is the one in East Hartford, Connecticut on our weathering steel bridge. We had about 50 beam ends repaired here. The bridge was a mix of simple and continuous spans. We were only doing the repairs where we had the joints, so at all of those simple ends. And once again, this was on I-84. So in Connecticut, we have our 3 major interstate systems, and we got to do 2 of the 3 in our first 2 trials. So this is another picture of one of the sides of the bridge. And here you can see the difference. So in the first project, we fully cleaned the beams and repainted them. Since we had weathering steel here, that wasn't done. We were only cleaning the area where the repair was going to go. And then you can see the other portion of the beam where we left that patina. So our condition, this bridge was also rated as structurally deficient. But here we had a really different corrosion pattern. So in the last project, it was really largely focused on, that kind of 6 inches above the web, but that local area roughly over the bearing stiffener. With this project, we had corrosion along, the bottom 6 inches or so that extended 10, sometimes up to 20 feet. So one of the concerns that this project had that was not seen in the other one was what's going on with this interface condition? How are we transferring that shear strength between, the bottom of the web and our bottom flange? So that's something that was considered in the design. Some of the differences in contracting in Connecticut, there's some design that's done internally, some that is sent out to consultants. So the first project was done by a consultant. The second one was done internally by the bridge design unit. And after the first project and some more research that we had done on the weathering steel test, we felt very confident switching to a performance-based specification. The DOT certainly wanted to move away from specifying any supplier, so we were able to shift to that performance-based specification. We did have to include some details on the partial height repair for finishing that top surface. We wanted to make sure there was no pooling of water on the top of the UHPC, because if that was going to happen, then we would have the same sort of corrosion occurring just on the top of the block. So we had to include a grade so the water would be able to flow off the top. Once again, including that mock-up just to make sure the same contractor did not get two jobs. So we were working with a new contractor, a new material, so that mock-up was definitely required. And once again, we did include instrumentation. So this site was a lot easier to work with without having to coordinate with rail, but still having to provide our team with access. So here's an overview of the repair design. Similar to the first repair, 5/8 diameter studs were used. We looked at the strength 1 load combination for capacity. Here's the stud equations that are represented in the guideline as well. And one of the nice things is that whereas the first bridge, we had a whole bunch of different parameters in terms of skew and beam height and types of beams that were used. In this project, we were able to use 2 standard stud layouts, and I'll show those more on other slides. And the UHPC we used here, Cortoff, was ultimately selected by the contractor with 2% fibers, and we had the same 28-day compressive strength noted in the specification as 18 KSI. One of the exciting things I really want to point out here is that you will have access to these slides, and we have the links. So all of the drawings for this project are posted online along with the specifications. So feel free to go to the DOT website and take a look at those. Moving on to our mock-up, since we were only doing a partial height repair, you can see this mock-up is a lot smaller than the other that we had used. One of the things that we did see with the weathering steel is that getting that nice weld around the stud was more challenging. So it took more tweaking of the gun and some of the settings, and the surface cleaning, I'd say, is even more paramount when working with the weathering steel. Also, this was the casting method that was used for the bridge. So we didn't have any sort of PVC distribution. It was much more simple. So we were able to just use those 5-gallon pails and fill the form. Looking at the stud welding in the field, this is where you can really see those 2 main differences in the standard layouts. In the first layout, this is when we had not as significant of a length of corrosion damage along that interface between the web and bottom flange. We only had 1 row of flange studs, and where we had a longer length of corrosion, we had those 2 rows of flange studs. Monitoring, we used the same sort of NEMA enclosures. The only thing is we limited some of our monitoring. We were able to look at the data we captured first, and then we're able to kind of scale it down, not use as many sensors to focus on the critical information. So we still were collecting our accelerations, our temperatures, and strain on the web studs and in the UHPC. And this is just a view of what that instrumentation layout looked like on the beam ends that we were monitoring. Forming was certainly much easier for the partial height repair. And one of the interesting things that you'll see here is for the partial height, this project also included replacement of some of those diaphragms, and those were lifted above the limits for the UHPC panel to prevent encasing any of the steel if future repairs were required. But otherwise, very similar forming with the plywood. We went with the same hole drilled through the back of the web, and then another rod going through the place between the gap and the webs of the beam on the same pier. For mixing, every material supplier, when we're using commercial mixes, has different methods that are preferred. So this is the one that was used by Cortoff, and it's mounted to a skid steer. Casting, we were able to just have a lot of those 5-gallon pails, lift them up with a boom lift, and fill from the top. And then the contractor did choose to go back and grind the surface to get the grade that was required, rather than doing any top forms. And here's an example of those cured beam ends, just following the state of Connecticut procedures. They also painted above the UHPC in that region, and that's kind of standard practice for weathering steel that they implemented. Another thing I'd like to note is just that hole that was left in the web that they went back and filled with, I'm not sure if it was either stainless steel or galvanized, but a corrosion protected bolt. A similar trend that we saw on our data collected, here you can see that we're getting smaller strains initially. This is because the level of corrosion in that barren column was not as high as the New Haven job. So where we were looking at over 200 microstrain, here we were starting at a max of about 30. So we did see a drop in the frequency of those high magnitude strain events. But one of the really interesting trends that we saw is we did have one location on the bridge that had a full perforation, and it was over a foot long. In here, what we saw, if we're looking at the web strain, is that initially we were getting almost no strain because there was no continuous load path. And after repair, that location was actually picking up additional strain. So we were able to kind of really re-engage that portion of the beam end, which was great to see. And then just looking at our other trends, still getting those same peaks of our web stud and concrete strain at whenever we're getting the truck passages. So then looking at some of our really important lessons learned, over the last 10 years, we've worked on developing the repair procedure for corroded steel beam ends using UHPC and thoroughly evaluating it through a series of experimental and finite element simulations. Moving on to the field work itself, and not to toot our own horn as the research team, but I think it was really important in the first couple implementations to be able to have the full team involved. We have an incredible relationship with the Connecticut DOT in working with them to make sure we had that really smooth transition from research to practice. And now we're at the point where they can move this forward without us. And some really crucial aspects of that implementation include make sure that you are thoroughly cleaning the area where the studs are going to be welded. One of the main causes that we saw from incomplete or low quality welds were from surface preparation that was not done according to the spec. So that's something that, the specification can be clean and tidy and think everything's really clear, but you still need to make sure that the inspector and the contractor are aware of the importance of that, and that's being looked into the field. Another big thing is, most contractors are used to using, kind of standard ceramic ferrules when they're shooting their shear studs for composite action, but it is different when we're shooting on a vertical surface. So sometimes this can just be kind of a slip of the mind to make sure that these are ordered when you're ordering the studs rather than them just including the standards. That was another thing that we saw in a couple of the field implementations, is just making sure that those proper ferrules are used. Once again, even though it's in the spec, just being on it in the field. And always, whenever you're using something new, include the mock-up. The lessons learned from that and how UHPC behaves and what's required of the formwork are really essential. It's much better to get a form that's leaking really badly when you're looking at a sample beam end than when you're on top of a bridge. Another thing is that we all know projects don't go exactly according to the plans. There's always going to be things that come up, field changes, corrosion that was worse or sometimes not as bad, mostly worse than noted in an inspection report. So it's super important, I'd say particularly that probably the designer and the inspector, I'd say are the main two, that they understand the structural performance of the repair and the material specific properties of UHPC. When you're trying to decide are additional studs needed, where to place additional studs, decisions like that have to happen in the field, you want to make sure that everyone feels really confident about how the repair is performing. So particularly what that load path looks like. And then we found, the two different repairs had completely different designs, UHPC mixes, casting procedures, different SKUs involved. And I think that all really goes to show the flexibility of the repair and that this is a great option for bridge owners. And just to show kind of how much more widely this is being used, I think this is numbers from maybe last month, but just shows all the different projects. So the two in green are the two that we showcased in this presentation, but there are several that are under, about 35 in design and construction across the state. So this is something that Connecticut has really taken and run with. And not only in Connecticut, this was included in the Everyday Counts 6 initiative. So this is something that's been used nationwide. And I know there's at least 5 or 6 states that had used it as of last year. I'm not even sure what it's up to now, but it's really taken off and it's exciting to see. Also want to include some links to some of the available design tools. So the ones that were prepared by our research team and any of their sample drawings are all hosted on the Connecticut DOT website. From EDC 6, there's also great materials that have come out of that that have, I think, a little more of that national perspective on it. And we also have some YouTube videos that show in more detail some of that repair process. And last but not least, I really want to thank, first and foremost, the Connecticut DOT for seeing the value in this, funding all 3 phases of the work, and being such incredible partners to work with. And of course, Arash Zaghi, he was actually my PhD advisor, now my colleague, but he was the principal investigator on all 3 phases of the research. Kai Willie as well, being involved on the UHPC end. And then our friends over at the Connecticut DOT in their research unit, as well as those involved in management, along with the design for the first project and the inspection for the second project. So really great team there. And of course, Mike and his group, they're heavily involved with the first repair implementation and the ideation, as he mentioned, and GM2 also involved in design. And then our contractors, being able to work with really 2 great contractors that were focused on collecting the information that we needed to be able to present at events like this and showcase what an amazing opportunity this repair provides. All right, and with that, I'll leave my slides up and hand it over to, I believe, Paul.
All right, thank you. Thanks for the great presentation. At this point, we are going to turn it to Paul to moderate the question and answer period. Paul.
All right, Atarid, Lexi, Mike, thank you. It's really a good presentation. We had a number of questions, probably about 14 that came in beforehand. It's now 1:55, and we were up to something like 22 or 23 questions that came in during the Q&A, and they're still coming in. So let's get started, and we'll try and go as quick as we can. First ones, I have some general questions that came in beforehand. Are there limits or thresholds for beam-in corrosion that possibly render this UHPC retrofit structurally undesirable?
Yeah, I'll take it. Lexi, you could jump in. Yeah, basically the premise is you need sufficient steel to weld the studs in place to transfer the shear between the UHPC and the beam end. So you need to have some decent web material left. So in some cases, if there's extensive corrosion, you might have to make the repair wider to engage more web. But that's the key thing. If the web is completely shot top to bottom, you're probably looking at a different repair.
Okay, thank you. Interesting question here. Can this material be used or this method be used as a preventative measure for steel beam ends?
It's funny, the deputy commissioner of the DOT at the time this research was going on, that was her question. It's a great question. The answer is, of course you could. It hasn't been done yet, but it's something we've talked about.
I'm working on it. I have a project right now where we're looking at. I just had a really great industry forum, which thank you for sending some CHA folks, Mike, but more to come on that.
The best solution is get rid of the bridge joint. That's the better solution.
Some people got some other questions about using this, and this is intriguing. would this be a useful application for steel box beam caps if
Yeah.
you've got corrosion going on in those things?
Well, if you have corrosion, I guess yes. The answer could be you could use it definitely for a repair. I mean, anywhere you want to transfer force between one plate and another, this material is awesome. The second project that Lexi described was a good example of interface shear transfer. So if you had a box beam with corrosion between the web and the flange, you could definitely use this and do a similar repair. It's a great material that can be used really in many different locations. And there are actually other designs that are being constructed right now in Connecticut that are different than what we showed using UHPC. So more to come.
Okay, well, here's another one.
Yeah.
Similar corrosion can be found on connections of floor beams to main girders for railroad through girders. Can this same concept be used for the floor beam to main girder connections?
I don't see a reason why not. Really, the sky's the limit of how you can do this repair. Anywhere you're going to bolt a plate on to do a repair, you can consider using UHPC to do the same.
Okay. We'll get back down to some smaller questions now, the big concept questions. In using this method of repair, what is to be done with the bridge bearings under the repaired beams?
Yeah, this is a more general question. I'll take this. Basically, you don't have to replace the bearing. If you're planning on replacing the bearing, fine. But the real goal to this repair is to repair a steel beam end without jacking the bridge up. To replace the bearing, you obviously have to jack the structure up. So in most cases, we're just looking at the fascia beam of a multi-girder bridge because that's where the corrosion exists near the gutter line. So we're not looking at jacking the entire structure. Of course, you could, but if your bearing is salvageable and you want to just keep the old bearing in place, you can do. That's the idea behind this repair. But you could do it either way.
Yeah, and just to point to the two projects that we did, the first full height did include bearing replacements. The second project did not.
Okay, there were some comments on that. Let's see. We'll just go down the list here. Was any consideration given to eliminating the deck joints as part of the repair to minimize future corrosion?
Always. To try to get rid of the joint, either get rid of it with a link slab or to replace the joint with a new joint that doesn't leak. Number one source of corrosion on bridges. So anything you could do to the joints, but it's not necessarily coupled with this repair. You literally could do this repair and not repair the deck joint. And as Lexi mentioned, the research looked at corrosion of this repair and found that even exposed to significant corrosive environments, this repair is a very durable repair.
Okay. Then let's see for some design questions. This one came in before the webinar. Are there any concerns with the difference in material properties between the UHPC and the steel for this construction type?
I mean, my opinion is it's just like any composite structure. You have to look at transformed sections. The AASHTO is going to be publishing a guide specification for UHPC, which will give more information on material properties to use. But strain compatibility is the approach that's used, like any composite bridge. So really, the design is like any other composite design. There's no real difference.
Okay. How does this repair affect the load rating for shear of the repaired member?
Lexi, you want to take this one? I don't answer all the questions. You can answer.
I mean, you're doing it so quickly, though. Keep going, Mike. I'm just going to nod along. I'll jump in if I ever want to add.
Yeah, the basis of the repair is to fully restore the shear capacity at the end of the beam. So really, it's as far as the load rating, you could basically rate the bridge as if the bridge is pristine and the repair wasn't even done. Essentially, we're replacing the bearing stiffener with this UHPC column. Rating the bridge, it should rate the same as if it's undamaged.
Okay. What considerations or details are used to account for skew, and how do you work around the end diaphragms?
Yeah, that's a great question. We've looked at this, and at the first bridge in the Haven, I worked with the designer a little bit on how to handle this. The issue with skew is getting the shear stud gun in there to make the welded shear connector connection. In the acute corners, it can be really difficult to get in there with the end diaphragm. So UConn did research looking at other options where you could go in on the obtuse side of the girder where you get much better access. You could drill a hole through the web and install a high-strength bolt with double nuts or a threaded rod with double nuts. I believe, Lexi, the research showed that the capacity was the same as the welded stud. And so there are ways of getting around it really comes down to getting the shear studs in. That's the hard part.
Yep, absolutely. We did get good results. We did have higher kind of deformations between the two, just with some of the threaded bar. But I think in New Haven, we were able to get the gun in a lot of places, and then we just did kind of standard welding around the studs right at that acute corner behind the C shape.
Okay.
Yeah, I believe the Yukon research also looked at just drilling a hole through the web and not even putting a stud in, and look at the shear of the UHPC through that hole, and found out that it did a significant amount of shear transfer. It wasn't sufficient, it wasn't equal to a shear stud, but it was, just drilling a hole, letting the UHPC take the shear as opposed to the stud taking the shear. But no, either the threaded rod or the studs are probably the way to go if you can't get a stud welding gun in there.
Okay. Question here about does Connecticut DOT have standard UHPC specifications for this type of construction?
Yeah, I believe in the second project, Lexi, they developed a standard special provision that is non-proprietary. It's essentially a performance spec for the UHPC. So as now we have multiple manufacturers in the market, so we're not just using a proprietary mix from a specific company. So that's opened the door for quite a bit more competition, hopefully lower prices.
Yes, and I can put the link to that on the spreadsheet when we post on the website after, but that's all posted on one of the links that I included.
Okay. And then are certifications required for installation personnel regarding this type of construction? You said they had to attend a pre-bid meeting, I guess, or something, and then but were there any certification? I guess the welders have to be certified. Anything else?
Yeah, welders, but as far as the installation of the UHPC, Lexi hit the nail on the head. The key is to have a mock-up, to have the contractor practice a mock-up to make sure that they can execute the repair before they actually repair the actual bridge. We did a mock-up recently on a project in Connecticut, another project, and the first mock-up didn't go so well, so we did a second one, and the second one was fine. So that's the way we do. The contractor can learn on the job using these mock-ups. It's a difficult material to work with, but it's not that difficult. A little bit of practice, and the results are fine.
Okay. If the deck is not replaced, how do you place and remove the forms for pouring the UHPC in such tight confinement, particularly adjacent to the back walls?
Mm-hmm. Well, Lexi showed pictures of the two examples. They were able to work around the end diaphragms and the ends of the beam. So there's ways of getting around it. One thing that was shown is shown how the UHPC was pouring through the top of the deck, which really facilitates placement. If you could take a lane at night, say, to do that pour. We have actually talked about detailing. We're allowing the contractor to core through the top flange of the girder at the end, even greatly simplifying it, where they don't have to have the PVC piping. They can just pour right through the top flange, right into the UHPC column from the top down. So there's multiple ways of doing this. There's contractor means and methods. Contractors, I don't think, had any issue forming these things. There's always a way of getting in there to form it. Let the contractors get creative, and it's really not a big issue.
And I personally, I love the detail of coring through the top flange.
Okay.
Yeah. Well, we don't need the top flange. Yeah, so might as well go through it.
Question came in both beforehand and during the presentation about how do you cast the UHPC and ensure that it gets contact with the underside of the top flange, bottom of the top flange?
Well, the key thing is, in most cases, we don't need to have that contact with the top flange. We're trying to transfer the shear from the bearing into the web of the girder. By the time you get to the top flange, you've transferred that shear. So it's not, and the partial height tests that were done in the lab proved that out, that you really don't have to go right up to the top flange. And if you take the forms off and there's a slight gap there, it is not the end of the world at all. The shear has already been transferred.
Okay.
And if you really want it, you just need to have enough of that pressure head. So if you're coring through the top, you don't want to do a separate deck repair after that. So just fill the core hole with UHPC, and it's going to be stronger than it was before.
Okay, we had a number of questions on the studs. It says, what is the function of the stud structurally, and how do the studs participate in the load path, especially if they are welded to corroded web with section loss?
You want to start, Lexi, on that one?
Yeah, sure. So that's a great question. Our goal is, we know there's going to be some level of corrosion at the end, but you really want to weld the studs to a solidly intact portion of the web. We had examples where there was more corrosion, and really the stud gun will just punch through if you don't have enough web there. So once we weld to that intact portion, as the load's coming through, it goes through the studs into the UHPC, and then the UHPC really sends that bearing force directly into the bearing. So it's the stud in shear that is transferring the load. In the stud itself, we're not going to get failure of the UHPC. It's going to be shear failure of the stud if there's not enough studs.
Okay.
And the interesting thing with UHPC, the shear failure mechanism for the stud is different than with normal concrete. Normal concrete, we have crushing of the concrete around the stud. In UHPC, I believe the weld is the critical, almost the critical failure mechanism. The actual weld fails because the stuff is so strong. But the research at UConn, we have numbers on how to design that, the capacity for the UHPC, the stud in UHPC.
Okay. How do you measure the amount of steel lost by corrosion and cleaning up? Will this dictate the length and thickness of the UHPC?
That's a great question. For the length and thickness of the UHPC, no. The thickness is really from cover from the top of the studs or from ease of forming that we get that thickness of the panel. And for the designs that we suggest, we're either normally designing for kind of the full strength one load or only the live load. So it really, we're not counting on any really residual performance of the web. So
right. Yeah, we designed for the entire
much.
reaction of the girder. We'd assume that the bottom portion of the girder is gone completely, and it just takes a few more studs. If you say, well, maybe there's 20% web left, let's count on 20%. It's almost just as easy to say 100% of the loss in the web and the bearing stiffener and design for the worst case. It adds 1 or 2 more studs. It's not a big deal. So it's not worth trying to figure out how much steel you have left. So when you're in a design office, you haven't cleaned the steel off. You don't know exactly what the section loss is. Just assume 100% and go with that design.
Okay, then there was a question, are the shear studs welded outside of the corroded area, or can you weld it a little bit into the corroded area?
It depends how much, like what the remaining web thickness is. You know, we can get down lower, but it's basically you have to have something left for it to not blow through. And if we do have regions that are really heavily corroded, we have welded on the bearing stiffener if there's more meat to that in locations where it's really bad.
Interesting, University of Massachusetts did a study for Mass DOT looking at corrosion patterns for steel beam ends. It was a very good complementary research project they did. And they looked at thousands of inspection reports for beam ends that were corroded, and they've established standard, not standard, but common corrosion patterns of steel beam ends. And in virtually every situation, there's intact web above the bottom of the beam that you can weld studs to. So this repair can work in virtually every case that we've seen. But it was a very good complementary research project done at UMass looking at that. And they also did research on how to calculate the capacity of a corroded beam end without the repair to see if you need to do a repair. So it's a very excellent complementary research project done by UMass.
Okay. Is there a percentage of rust that will decide if this method will work or not?
Well, again, there's usually intact steel in the area, so I've never seen a case where we couldn't get in there and do the repair. As long as there's intact steel to weld the studs above the corroded area, the repair will work.
Okay. We're at 10 after, so I'm going to go ahead and we still have a whole lot more questions. I'm going to turn it over to Rick, and he's going to.
I'm trying to answer them as fast as we can.
Okay.
Yeah, there's a lot of questions rolling in, Mike, so you'll be busy for a while here. But one question that I thought that came in recent here was, is the jacketing with the UHPC stop the propagation of corrosion along the steel beam, long-term, I guess, the long-term performance type thing?
Based on my experience, a concrete encased steel beam is very durable, and we feel that the repair, combined with the painting that Lexi showed in those projects, that you've essentially taken care of the problem for long term.
Because that was one of the other questions was, is the area, painted before the UHPC, or primed or painted before the UHPC is applied? So.
Yeah, and I'd say underneath the UHPC, no. We know that's enough protection, but if you're doing a partial height, then yes.
Okay.
I guess the real answer, to add on to that, is we're not counting on the bond of the UHPC to the steel to transfer shear. We're assuming the shear is being transferred through the studs only. So, it's a little bit of paint and the interface around the edges is not a problem because we're assuming there's no transfer.
Yeah, there was a number of questions that you already answered, Mike, but I didn't know if you want to say any more about the using bolts or rods in place of shear studs.
Yeah,
So,
yeah, we covered that. I believe that the document you produced, Lexi, does include information on that as well. If not, you could contact UConn and find out.
Yeah, we have other research on that, plenty of research papers. I would say the overwhelming amount, and I think the best approach is to use the studs. That's what our research focused on. But if there's unique situations, or you're talking more of, you know, a repair that you only need for a couple of years, there's a lot that you can do in that realm.
so how has follow-up inspections of these repairs, you know, what have you seen with, and how much follow-up has been done?
So yep, particularly with the first project, you know, it finished in 2020. There's been at least one inspection cycle on that, and I think the second one as well. No issues so far.
Okay. Now, has there been any modeling to interface the, you know, I'm sure this, you know, the whole finite element modeling thing, right? As far as the interaction between this substrate and the UHPC and compared to what you obviously measured and monitored. Has that been done at all, or?
So there's been a lot of finite element modeling on the more simplistic experimental studies, and we're working on some for the field implementations to tie that with the data now.
Okay. There was a couple of questions, or one question came up was, is this a possibility for repairing a bottom flange that's severely corroded? And that's, I see Mike nodding his head there. So.
Yeah. Oh, the answer is, though, I mentioned in the beginning, is usually at a beam end, there's almost no bending moment. So even with a 50% second loss in the bottom flange, it's usually not an issue. We have a project right now in construction, repairing a bottom flange at a pier and a continuous bridge that had corrosion. We're doing a similar repair there as well. So we're actually adding UHPC on top of the bottom flange through the bearing stiffener across the pier. And the sky's the limit. You once you have material properties of this material and know how to transfer force from the UHPC to the steel, really it opens up a whole realm of possibilities for how to repair. And we've been working with Federal Highway. They've done a great job with their EDC6 program, working with Federal Highway to come up with ideas for repairing beam ends. So maybe a future webinar we'll talk about that repair. But there's a lot of ideas where you can use this very flexible material.
So there was, and I can't find the exact question, there's so many here to sort through, but about fatigue, you know, installing shear studs does, you know, have an impact on fatigue category, but I guess that question is kind of floating out there. So
yeah, it's just, you're at the end of the beam, the live load stress is almost zero. So really it's not an issue. If you're dealing with a tension flange in a high stress area, then yeah, you would have the same fatigue category as you would with a welded stud, which I believe is category C. So you'd have to check that. But we're doing repairs where the stress is virtually almost zero, and fatigue really is not an issue. But if you were concerned with it, you just do the same standard ASHTO design for fatigue with a shear connector.
Shear
and I think
Federal
Highway, I want to say, is putting out some research, if it's not out already, on the fatigue of studs in UHPC.
Okay.
Or I know they're working on it. So.
Yeah, so I was talking more fatigue of the girder, but that's great.
Yeah.
That there's also research on fatigue of the stud.
Yep, so we're at 2:15. So thank you very much. A lot of positive comments about it and your presentation and great information. So
thanks
for back to Kathy.
We'll be answering questions that came in at a later date and posting them online.
So anyway, so Mike and Lexi, thanks for the great presentation. Lots of useful information from the research to the practice, and we appreciate the time that you took and to give this presentation again. Just as a last note, please take a look at some of the announcement that's out there for the submitting an abstract for the 2024 World Bridge Engineering Conference. That's going to be held actually at the Hilton Hotel in Miami, downtown Miami, Florida. So on that note, we'll conclude this webinar and hope to have you again with us during our next month webinar. Thank you and happy holidays.